Welcome to our seminar on what to know about LiFePO lithium iron phosphate marine batteries. Depending on the media you're using, the slide presentation will progress automatically, or you can move it using your arrow keys or perhaps the enter key. My name is Tom Trimmer. I am a founder of Custom Marine Products. At Custom Marine Products, we specialize in marine solar systems and in battery power systems. I am a cruising sailor, have been for over 30 years, so I'm familiar with the importance of having sufficient power on board. Let's take a look at what we're going to cover in this presentation. I'm going to provide you with an overview of lithium iron phosphate battery technology, so you understand some of the buzzwords, if you will. We're going to look at the performance characteristics of these batteries and compare them to lead acid batteries so you can see the advantages and disadvantages. We're then going to go through a design exercise in how to design a lithium iron phosphate battery bank for your boat. And we'll talk about some installation considerations and summarize the advantages and disadvantages. The slides in this presentation are available on our website at custommarineproducts.com, either on the battery webpage or under Products, Manuals, and Info. So you can use this slide presentation as a reference later on. First, let's take a look at lithium iron phosphate batteries and what it's composed of. The LiFePO comes from Li for lithium, Fe for iron, and PO for phosphate. Lithium iron phosphate is the primary content of the cells used in the battery. Lithium iron phosphate is a chemistry that has excellent thermal and structural stability, and so it's ideal for a marine environment. The second component of a LiFePO battery is the battery management system, or BMS. This is basically a computer that is included in the battery, connected to the cells, and protects the cells, ensures that they're charged and discharged properly, and controls the overall performance of the battery. These are then sealed in a case, and you have a LiFePO battery. Let's talk about some things we need to know about LiFePO cells in the battery. So LiFePO lithium iron phosphate is also referred to as LFP. And this chemistry has many advantages. For example, the high thermal and chemical stability means that it will not catch fire and is very reliable. The cells can be charged and discharged many times. In fact, over 2,000, sometimes up to 4,000 or 5,000 charging cycles. Because they discharge at a constant voltage, there is full power supplied to our appliances as the battery is being discharged, so they run more efficiently. The energy density is literally double that of lead acid, which is the amount of power you can store per weight. The low discharge rate of these means that they can be stored for a period of time without having to be trickle charged. And they are very rapid and efficient charging, literally 20% more efficient than lead acid. This means that more of the power captured, for example, from a solar system or wind generator is stored in the battery. The battery has a few disadvantages in that they're not to be used in very cold environments. Their life can be shortened, used in very cold environments. And they are expensive, so there's a fairly high investment in them initially, but the advantages and the longevity offset that. There are various different types of LFP cells. Here are two common numbers, common cell types used in lithium iron phosphate batteries. So where does the 4 come from in lithium iron phosphate 4? Well, the 4 comes from 4 cells in series. Each LFP cell is 3.2 volts. And these 4 cells are wired in series, and then each series set is wired in parallel to achieve the battery capacity desired. So in this diagram, you can see 4 cells and 4 cells, and each of these groups of 4 then are wired in parallel to form a lithium iron phosphate 4 or 12 volt cell. There's a LiFePO4, which would be a 24 volt cell. Let's talk about a battery management system, or BMS. The BMS regulates the power, charge, and discharge of the battery, and it protects the cells from being damaged. Now, this power regulation enables cell protection in a number of ways. It prevents over and under volt, it monitors voltage, charge, and discharge, and prevents a battery from being overcharged or over discharged. It can also monitor the temperature and prevent charging or discharging at very high or very low temperatures. The BMS also controls the maximum current draw, or the maximum draw that can be pulled from a battery. This is very important for our marine applications in that we want to be able to pull a fair amount of current if we're driving a windlass or an electric winch or something like that that has high current draw. We need high current draw on our boats, and a high current draw also implies high current charge, so we can do rapid charging. And also the BMS will automatically shut down if there's a short circuit in the battery, so it can't be harmed. Also, it regulates the cell charging so that all the cells maintain the same level of charge. This is called cell balancing. So we want all of our cells to be roughly the same charge and evenly balanced. It enables a drop-in capability to replace lead acid or AGM batteries. So an easy replacement of these batteries. So the battery management system makes the lithium iron phosphate battery perform in some of the same ways as lead acid and AGM for both charging and discharging. And finally, the BMS, because it's connected directly to the cells, can monitor the state of charge and report it either with a Bluetooth app on your smartphone or a meter built into the battery. So we're going to talk about that also in more detail. Let's look at the rate of discharge, or what a discharge curve looks like. For lead acid, we see a discharge curve where the voltage decreases as the lead acid is discharged, and we can usually discharge it to about 50% without damaging the battery. On the other hand, the discharge curve of a lithium iron phosphate battery is relatively flat. So appliances receive a higher voltage all the way through the discharge process and run more efficiently. Literally 95% of the capacity is used versus 50% for lead acid. Now, the voltmeter does not necessarily give us a good indication of our state of charge as it would with a lead acid battery. And we're going to look at that in just a moment. I did want to address the concept of C. As you're looking through various documentation, you'll see C. Well, C is the amp hour rating of the battery. So in this case, we're looking at a 12.8 volt, 100 amp hour battery discharged at the rate of 0.2 C, or if you will, 0.2 or 20 amp discharge rate. Why is a Bluetooth monitor important, in our opinion, for marine applications? Well, we said the discharge curve is very flat. So the meter, a voltmeter, isn't going to tell us very much about the charge and discharge. It's only going to be within a couple of tenths of a volt. So with the battery management system, because it knows everything that's going on, we can plug in a Bluetooth capability and monitor from our smartphone. And we can have a tremendous amount of information about the battery. We can see the current and voltage charge or discharge. We can see if it is in a charge or discharge mode. We can see a state of charge, which says that we have, in this case, 94% of the battery charge remaining, and we're pulling out 3.98 amps out of the battery. A second page of this will actually tell us how many minutes we have left if we continue to discharge at this rate, or if we're in charging mode, it would tell us how many minutes to a full charge of the battery. It'll tell us the temperature of the battery and give us some graphics on how much power we have remaining in our battery. So it'll also tell us our charge cycles. So here this battery in this example has been gone through 18 charge-discharge cycles. We're going to talk about these charge cycles some more because it's a very important point. So we like Bluetooth monitoring of our batteries. If we compare the charge and discharge of batteries of lead acid versus LiFePO, they look quite different, the charge curves. So if we look at lead acid, we have 3 phases of charge. We have what's called a bulk charge, where the battery is taking a maximum amount of current that it can accept to get up to a voltage of maybe 12.8 volts. That voltage is held constant, but as the lead acid charges, its charging efficiency decreases and it can accept less current. So over a period of time, we really can't get as much current or power into the battery as it becomes more inefficient. Then once it's charged, we need to go into a float mode to give it a slower charge for that last 10%. On the other hand, a lithium iron phosphate will come up to charge very quickly, up to voltage, and maintain that constant voltage all through the charge process. And it will accept, and this is the key, a constant current, maximum current, all the way through the charge process until its full current is reached. And then if your charger is so designed, it can put a slight float mode on that battery to just top off that top 1 or 2%. So because we can charge with this constant current, the LiFePO battery is much more efficient in charging, and that efficiency means you can store more power faster than a lithium iron phosphate battery. There are many different performance curves and things to analyze. We're not going to go through all of these in detail during this presentation, but I did want to point out that the depth of discharge chart is very interesting in these. And basically what this says is that if we discharge our battery 100% at a given rate, we'll still get 2,000 charge-discharge cycles out of the battery. If, on the other hand, we draw it down 80%, we'll get upwards of 60,000 or 6,000 charge cycles. And if we only draw it down 50%, you can get over 100,000. So the amount you draw it down will affect the number of charge cycles, but it is still, you're looking at 2,000 to 6,000 charge cycles, whereas a lead acid, you may only get 300 to 400 charge cycles. So you get 10 times the charge cycles out of these batteries. They also measure a pretty constant current depending on how rapidly you discharge the battery. So if we discharge it here at 0.2 C or 20 amps for a 100 amp hour battery, you're going to have a pretty constant discharge. If you discharge it at 0.5 C, or you're pulling 50 amps out of it, you're going to have still a pretty constant voltage before it drops off. So the lithium iron phosphate batteries hold a pretty constant voltage regardless of how fast they're charged and or discharged, and they have a very high life cycle or number of cycles depending on how deeply they are discharged. Temperature is a key factor in LiFePO batteries. These will not be a good option if you're sailing to the North Pole. You want your charge temperature to be between freezing and about 113 Fahrenheit. The discharge temperature or the usage can discharge it at a -4 degrees, and storage is fairly wide range for storage. Now these are typical parameters provided by the manufacturer. In the testing they're fairly conservative. So let's say that you're going to charge this battery not at 32 degrees but at 20 degrees Fahrenheit, really cold. The battery will still take the charge. What you're doing is you're reducing the number of charge cycles. So you may bring the charge cycles down from, say, 3,000 to maybe 2,800 or something like that. So also it's important to note that unlike lead acid, the charging and discharging does not generate heat within the battery. So these batteries stay cool all the time, so a temperature sensor is not necessary for charging. Here's an example of what the specification sheet might look like for different batteries. So you have the amp hour rating of the battery, like a 120 amp hour battery at 12.8 volts, which gives you your wattage. Amps times volts is watts, so you have your wattage, and then it'll tell you the number of cycles. So in this case, these batteries are examples of customary products, CMPower batteries, 2,000 rated at 2,000 cycles if you fully discharge them, 3,000 cycles if you charge them to 80% depth of discharge. They'll discharge less than 3% a month. And then we have our charge voltage, and a key factor here, an optimum charge current, which is between 0.2 and 0.5 C. So for a 100 amp hour battery, 0.2 would be 20 amps to 0.5 C, which is 50 amps. So the charge current that these batteries will take is pretty big, pretty significant. So you can pour a lot of power into these very quickly. The continuous current is how much current can you draw from these continuously and still keep your number of charge cycles high. Now, many batteries are typically 100 amp, 80 to 100 amp continuous discharge. We put 150 to 120 amp continuous discharge in most of our batteries, and you can look at it as making them heavy duty. So if I've got something where I'm running my windlass and something else, and I need to start my engine with these batteries in a hurry, I need to be able to pull out a lot of power. And so for marine use, we think 120 to 150 amp max discharge is really important. Also, we have our temperatures that we can operate under and battery sizes. So these are the kinds of things that you see in battery specifications. Now let's compare lead acid to lithium iron phosphate batteries. This diagram kind of tells the story, I think. With lead acid, we typically don't use the bottom 50%. We only draw them down 50% to keep the battery healthy. We then, when we're charging, that top 10%, as you may know, is very hard to get and takes a long time. That's because the battery is very inefficient in charging that top 10%. So quite often with a lead acid battery, we only get 40% of its rating. So if I have a 100 amp hour lead acid battery, usable amp hours is really 40 to 50 usable amp hours. In contrast, a lithium iron phosphate battery can easily be drawn down 90 to 95% and still keep a high number of charge cycles. So we don't often draw it down to full, but we can. So literally on a 100 amp hour lithium iron phosphate battery, we have 90 to 95 usable amp hours, or almost double that of the same type of lead acid battery. Likewise, the weight is significantly different. A lead acid battery of 100 amp hours is typically around 65 pounds. A lithium iron phosphate battery is only 31 pounds. So we've got literally double the amp hours stored at half of the weight, which means our energy density is anywhere from 4 to 10 times that of a lead acid battery, which energy density can be measured in watt hours per pound. The number of charge cycles we've talked about, typically on a lead acid, a charge cycle being drawn down to at 80% of its capacity and then recharged. Or in the lithium iron phosphate, 2000 number is drawing down 90 to 95%. So we have literally 10 times the charge cycles. And I say 10 times because if we drew down the lead acid 50%, we'd get about 400 charge cycles. If we drew down the lithium iron phosphate, that's just the 50%, we would have literally 4,000 charge cycles. So it's literally 10 times the length. The charge efficiency of these batteries is also quite different. The 70 to 80% charge efficiency of lead acid versus the 99% charge efficiency of lithium iron phosphate is very significant. What that means is that 20 to 30% difference is 20 to 30% more power from your solar system or wind generator or alternator going into and being captured by the battery. So this is significant in both the amount of power that is stored, that is generated to be stored, and also the speed at which it is stored. Also, it's important to note that the battery, the lead acid battery, will discharge or self-discharge, if you will, upwards of 20% a month, whereas the lithium iron phosphate is less than 3% a month. So that winter storage or long-term storage is not an issue, and you don't need to put a trickle charger on the system. Now let's begin to design a battery system for your boat. I'm going to take you through the process so you can do this on your own boat. The first thing we need to do is determine our power usage in a 24-hour period. And we determine that by looking at the amp hours of use of each appliance. So refrigeration, for example, being 5 amp hours draw, and if it runs for 10 hours, the system computes that we would consume 50 amp hours in a 24-hour period of power to drive that refrigeration. We do that for each appliance on the boat, coming down to a total amp hour usage for our DC part of our boat at 71.5 amp hours. We can do the same on passage by taking our amps times the on passage usage hours to get our daily 24-hour usage while we're under passage. If we look at AC, quite often AC appliances are measured in watt hours used, or watts. And so if we add, for example, through an inverter and a microwave that draws 1100 watts, and we use it for 1/10 of an hour, the system computes 10.2. So we come down to a total of 81.7 amp hours used while at anchor and 176.8 used while underway on passage. If we assume we're at a 13 volt charge for our 12 volt system, we can see that our watt hours consumed per day is about 1,000, a little over 1,000. Under passage, about 2,200. Now we use these numbers on the following screen. Where we determine, here we're going to determine our days of reserve capacity desired. In other words, if we're at anchor, how many days do we want to run off of our battery without having to recharge it? So if we say that we're going to run we want to be able to run 2 days, our lithium iron phosphate batteries, we can draw them down. Let's say we want to draw them down 90%. This tells us then that we need a battery capacity of 181 amp hours. That's how many usable amp hours we need from that battery. So if we use a 120 amp hour battery, the system tells us that we need a battery and a half, or we round that up to 2 batteries. Under passage, we would need 4 batteries to go 2 days under passage. If we look at lead acid, where we can only draw down 50% for a same capacity, 120 amp hour rated battery, we see that we would need 3 batteries instead of 2 batteries. So we can use this worksheet and this methodology to compute how many batteries we need. Let's take a look at our options for wiring our battery bank for our boat. In this example, we're going to use batteries with a capacity of 100 amp hours and a voltage of 12 volts. And we're going to say that the continuous current, or the continuous current draw, the amount that we can draw from the batteries, is 100 amp hours at a time. So if we wire 4 of these in parallel, we would have a 12 volt system. We add the continuous current, which means we could pull a maximum of 400 amps out of this system without damaging or reducing the charge cycles of the battery, for a capacity of 360 amp hours at 90% discharge. On the other hand, if we take these 4 batteries, we wire them in series, we have a 48 volt battery system. Our maximum draw, continuous draw, is 100. We can pull 100 amps out of the system at any one time. So I contrast this, the 400 amps in a parallel system draw, so it's additive, versus 100 in series, whereas the voltage is additive across on series. So they both banks have a 360 amp hour capacity at a 90% full draw, but the amount of power that we can draw and the voltage rating is different between series and parallel. So the CMPower, the CMPower batteries, we put a BMS in that will allow up to 10 batteries in parallel and up to 4 batteries in series. So then we also recommend, and this is very important, we're going to talk about this more later, batteries should be about the same state of charge when we wire them together, within 3 to 5% state of charge when we wire them together. An abrupt interruption of the load on an alternator that is putting out a full current could cause a voltage spike that could either damage the alternator or possibly damage sensitive electronic equipment. Now, this could happen when a heavy load is immediately shut off, or for example, when the 1-2 both battery selector switch is defective and different batteries are selected, or when a BMS shuts off when the full battery voltage is achieved. So such an interruption could happen when the BMS shuts off charging these batteries. And there is a way to take care of this. This doesn't happen with all BMS units. In fact, the CMPower BMS does shut off slowly, so there is not as much of a spike. However, if this is a concern, there is a solution. It's the Sterling Power Alternator Protection device, and it absorbs that voltage spike and costs less than $90 and is a good idea to put in if you're concerned about the alternator being damaged by the BMS shutting down quickly. Now, not all BMSs do this abrupt cutoff. And another thing to consider is if you have a number of batteries wired in parallel, they're not going to all shut off instantly at the same time. Now, the shut-off time we're talking about here is in seconds or tenths of a second, not a long period of time, to give the alternator time to shut down without a voltage spike. So in a group of batteries, let's say our 4 batteries are wired in parallel, each one is going to shut down as it reaches its peak voltage. The last one would be the amount of shock, if you will, to the alternator, which would be relatively minor. So this issue is not necessarily a significant problem, but could be depending on the BMS used in the battery bank and is taken care of by the Sterling Power device. And it can be obtained at sterlingpower.com. So here's some installation considerations. The nice thing about these batteries is that there's no fluid in them, and so they can be mounted on their bottom, their side, any side, so you can mount them in any way you wish. We suggest that they not be mounted in an engine room where they're going to get very warm. It's much better in a moderate temperature environment than in a hot engine room for the overall life of the battery. We suggest that you, same as with a lead acid or AGM battery, that you fuse the positive wires per the ABYC standards. And we suggest, as I mentioned earlier, that they be within a 3 to 5% state of charge of each other before connecting them together in series or parallel. Now, we're also often asked the question, can I combine my lead acid with my lithium iron phosphate? And the answer is no. The reason it goes back to our performance of these batteries. They charge in a different fashion and they discharge in a different fashion. So while they're compatible with the chargers and they have their own discharge performance, they're not compatible to be wired together. They're quite different. If you have a battery monitor on board, which means you would have a shunt somewhere where the negative of the battery goes into the shunt, and then on the other side of the shunt are your charging systems and your house draw. These battery monitors typically program for lead acid with this Pukert constant of about 1.25, and that it compensates for the inefficiencies in charging the battery. Because lithium iron phosphate is so much more efficient than lead acid, you'll want to change your scale in your battery monitor to 1.04 or even 1.03 so that the battery monitor is not compensating for this tremendous inefficiency that lead acid batteries have. You may also need to change some of the charging parameters in your charging sources. So let's take a look at what these parameters might be. And these will, while you can use your lead acid charge, most lead acid chargers to get optimum performance, here are the parameters that you'll want to program. The absorption length of time, or the absorption voltage, is for these batteries is typically 14.4. You could go up to 14.6, but these batteries like a 14.4 absorption voltage. Lead acid is less than that, but some AGMs are close to that. The absorption time is recommended at a half hour per 100 amp hours of the battery. So if I have 200 amp hour batteries, I'd set the absorption length of time to 1 hour. Lead acid, this is often much longer, so you can use a shorter absorption time for these batteries. The float voltage, float isn't really necessary with lithium iron phosphate, but if you have a float voltage, we suggest 3.5 volts for a float. 3.6 or lower is perfectly acceptable. Your chargers doing a float phase with these batteries is certainly not a problem. Equalization, on the other hand, we do not want to equalize. Equalization is typically up around 15 plus volts. These batteries do not need equalization. The purpose of equalization is to knock the sulfates down on that form on the lead plates. Well, these batteries don't have anything like that. So turn equalization off. If it can't be turned off, set it at 14.4. Temperature compensation with these batteries is not needed because they do not heat up as they're being charged. So the temperature compensation sensors just aren't necessary. And if you have a temperature cutoff on your charger, about -5 degrees Fahrenheit or centigrade, or 20 degrees Fahrenheit is a good cutoff temperature for full charge. So these are some of the settings you want to do. So let's just take a look at the advantages of lithium iron phosphate over lead acid as kind of a recap here. First of all, they're lighter than lead acid, literally half the weight or 4 times the energy density. Because they can be drawn down 95%, you have almost double the usable power in the same size battery of lithium iron phosphate versus lead acid. You can hold a steady voltage through that 95% discharge. So your appliances are going to run more efficiently, which means they're going to pull less power. Generally, these are plug compatible with your lead acid chargers. So installation is easy. We do, as we just talked about, recommend some reprogramming of the chargers if possible. Because they are more efficient in charging, they will charge more quickly than lead acid, so you have less charging time. This is really nice with the solar system. And because they charge more efficiently, more of your solar or wind generated power is actually captured in the battery versus a lead acid. So you have up to 10 times the charging cycles. So these batteries literally could last a lifetime. The batteries that I've had on my boat, I've had lithium iron phosphates on my boat for 2 years, and I've used about 18 charge cycles total. And these are going to be good for at least 2,000, possibly 4,000 to 5,000. We're going to talk about what that means here in just a minute. They are non-toxic, so they're safe. They have no fumes, no risk of fire, no acid to put holes in your clothes. They have very low self-discharging, so easy winter storage. We recommend a Bluetooth battery monitor built in, like we have in our batteries, so you can easily monitor the state of charge of your battery very accurately from your smartphone or your tablet. And they are very environmentally friendly in that they have no toxic chemicals or heavy metals. There are a few disadvantages of these batteries, and one is the operating temperature that we've talked about. You really don't want to discharge them below 4 degrees Fahrenheit. Some chargers may not be compatible with these, especially your older analog-based chargers. I wouldn't use them with lithium iron phosphate. Our initial investment is higher with lead acid, but the advantages and the longevity often offset this. We're implementing a concept of a battery exchange, putting it up, it's up on our website. So for example, the purpose of the battery exchange is, let's say you've used these batteries for 3-4 years, and you only have 200 or 300 charge cycles on them. Well, these are good for 4,000 or 5,000, 2,000 to 5,000 charge cycles. And let's say you're getting out of boating. What you can do is post your lithium iron phosphate batteries on our battery exchange and sell them as used batteries. Because our Bluetooth system reports the number of charge cycles and also reports if the battery's been abused by overcharging or undercharging, a customer can be very confident in buying your used battery that has many, many more life cycles in it. So it's a win-win. You get some money back for your battery. The new customer gets a battery with a whole lot of life at a could be a very inexpensive price. So that's the advantage of the high cycles of these batteries. There are a number of things to unlearn, if you will, when moving from lead acid to lithium iron phosphate marine batteries. For example, the voltage just does not decrease during the discharge of a battery. So you're going to see pretty much a constant voltage, regardless of the state of charge of the battery and regardless of how much power you're pulling from the battery. The battery charging to full is no longer really necessary. A 95% power rating means that you still have 50% to use. So it's no longer really necessary to charge the battery all the way to the top every time. In fact, these batteries really like to be run between 70 and 80% of capacity. Battery charging is different. There's no equalization. You have a shorter absorption change. So the charging is much simpler than what we're used to with lead acid. A state of charge of 50% is just fine because you still have 45% of your power still available. A faster, more efficient charging really is nice because it charges much faster and there's more power saved during the charging process. So it's amazing to see the additional power you can get from your solar system. The constant discharge of these batteries is interesting because the appliance run more efficiently, and I've seen my refrigeration run less time with these batteries. There's no toxicity, there's no water level to check, there's no acid holes in your pants, there's no heat to be concerned about, so maintenance is very simple, as is winter storage is very simple. I just disconnect the negative line wire on my battery and leave them for the winter, and I come back the next spring and the batteries are only down about 1 or 2%. It's easy to monitor and know your state of charge of your battery as your battery management system through Bluetooth tells you exactly what you need to know. When purchasing a lithium iron phosphate batteries, there's a number of things that you might want to look for. Clearly, the quality of the LiFePO4 cells is very important. There are a number of different quality cells out there. I will say that the Chinese own pretty much the lithium in the world, and they own most of the cell production. So even a battery that says made in USA has LiFePO4 cells made in China. The quality and functionality of the battery management system is also key. The better the battery management system, the easier it is to replace it with from the lead acid environment. The continuous discharge rate, as we've talked about, is very important. We consider 120 to 150 amp continuous discharge rate is important for marine batteries. It's kind of like buying a heavy duty battery. You can charge them with more power and they will discharge more efficiently, and they have the capacity for discharge should you want to use them for starting your engine or whatever. They'll do whatever you need to have done with the larger continuous discharge rate. you want to determine what the number of batteries to be wired in series or parallel. This is controlled by the quality of the BMS, so make sure that the BMS supports the number of batteries that you want to put in series or parallel. We've talked about the Bluetooth monitor, very important to understand your state of charge, and just a really nice thing to have. Compatibility with existing chargers is very important, and controllers. The warranty, our warranty is 5 years. I think it's very important. The battery exchange to protect your investment and be able to sell the battery as a used battery is a very nice thing to have. And clearly support. As you implement your battery system, you're going to have questions, and you want to be able to get answers to those. So things you'll look for are the amp hours of the battery, the voltage, of course, giving you your total watt hours, and then that all-important continuous discharge of the system. Here is a sample of specifications of batteries. These are our current battery offerings at CMP with our CMPower batteries. So we offer batteries 12 and 24 volt, including a start battery, although even our regular batteries can be used for start because they have the 120 to 150 amp continuous draw. So these are the batteries, the sizes, and the weights that we offer at Custom Marine Products. So thank you very much for attending this presentation. Here is some contact information for us at Custom Marine Products. Contact me anytime if you have questions about our products and questions about installing our products. You can reach me at tom@custommarineproducts.com or at my cell phone at 248-705-8337.